Hello, everyone. Today we're going to be talking common sources of RF power measurement uncertainty. So we're going to begin with taking a look at, we'll have the definition, and we'll take a look at the importance and some applications, an uncertainty budget example, and some of the most common sources of uncertainty that I see in mismatch, harmonics, and we're going to take a look at a few considerations to make to help improve our setups. So what is uncertainty? No measuring instrument is ever going to be perfectly accurate. When you're making a measurement, there's always some uncertainty, and that's the idea really behind, looking over at a thermometer on the wall and saying, okay, it's this exact temperature, or the understanding that there could be a range of values and a range of effects that could be playing into that, and it's roughly a certain temperature. So what I'm saying with that is the idea of the measurements without the uncertainty taken into account, like here, where we can see it's just more of an absolute point that we're putting down. And then when we're looking uncertainty, we actually take into account sort of a guard band to help account for these different variables with whether it's a measurement device or something to do with the system. So just to kind of think of it this way, for example, if someone asks, what is the temperature of this room? Well, we might say, it's about 23 degrees C. And the use of the word about implies that the room is not exactly 23 degrees, but we know it's somewhere near there. In other words, we recognize there's some doubt about the value of the temperature. We're trying to take that into account. So of course we could be a little more specific, and we could say it's 23 degrees Celsius, give or take a couple of degrees. And then again, we're saying give or take, and we're implying that there's still some doubt about this estimate. But this time we're actually assigning some limits to the extent of that doubt. And that's kind of the idea with the guard bands. So it's quite reasonable to assume that we may be, plus or minus somewhere within our estimate. But the larger the uncertainty we assign, we don't have a lot of confidence in that measurement. And the more that we can reduce all these different system variables, the more we're going to actually have statistical confidence in the measurement that we'll be taking. So before I go too far, I just want to take a quick moment to see what kind of field everyone's coming from, what your background might be as we get started in our discussion on uncertainty, steer the conversation a little more effectively for you all. So Donna, could you launch the poll, please?
Yeah, actually, this is Michelle. I'm going to launch the poll.
All right.
So what is your application that requires RF power measurements? So we're looking, medical, broadcast, communication, LMR, semiconductor, or other. So if everyone could vote.
And while everyone's taking a moment to submit their answer, I just want to start mentioning on some of the ideas about the importance of the uncertainty of the RF measurements. So the ones that come to mind immediately for me are going to be FCC limitations on irradiated power, so making sure you're within some sort of legal operating range, you're not stepping on anybody else's toes, and generating too much power that might be interfering with another signal. Making sure that while you're staying within those legal bounds, you're getting the maximum power delivered to your antenna, so you can help to ensure proper coverage area. If it's something where you're continuously monitoring a system, you want to make sure that your system appears to be operating within some specified performance limits. So in terms of system health monitoring, safety is another big one. I'm thinking particularly if you're a user who might be calibrating an MRI machine and making sure that we're going to be transferring, just the right amount of power into a human body and not putting them at risk. And then even the idea of effective process runs in the semiconductor world or other precision manufacturing. So let's take a look at those results. It looks like we closed the poll. Okay, so we've got a lot from
We've got a lot from
primarily from,
communication,
yep,
semiconductor, medical. So we have a good variety of folks out there today.
And
okay,
then
cool.
Steve, you gotta excuse my typo. That was me. Boradcast instead of
Oh,
broadcast. So, oh well, we're all human.
yeah, not a problem. All right, yeah, thank you everyone for sharing. So then, for you guys in the broadcast side of things or in the communication side, I'm sure you're typically thinking around those FCC limitations and making sure you have that proper coverage area. So just to kind of put some images with those ideas of those importance pieces, when we're thinking the idea of staying in that legal range of power and maintaining a reliable system, making sure that you have RF power accuracy is going to be always a critical thing. When it comes to safety for medical applications, I see guys doing different work from RF ablation techniques where they're literally burning off nerve endings and trying to apply a very specific amount of power to someone actually using an MRI machine to scan someone's body. There's a lot of limitations around things like specific absorption rate, making sure that you don't put too much RF energy into the body, you keep it at a safe level. And then in terms of accuracy, when we're thinking precision manufacturing applications like in the semiconductor world, where you might be etching very fine, narrow structures, where something like this could be, easily in the millimeters, micrometers, nanometers, very, very small, tiny structures, even down to when you're trying to deposit a very fine layer of material. So there's a lot of different reasons to consider, taking into account different portions of uncertainty to improve those RF measurements. So when I'm typically thinking of uncertainty, being on the vendor side of everything, I'm usually thinking in terms of uncertainty budgets that we have for our different, our sensors, our power sensors. So I figured this would be a great way to sort of start the discussion, taking a look at what goes into flushing out any types of variations that can be happening in a power measurement for a sensor. So this is our 7037 sensor, which is, as of right now, it's our highest accuracy sensor, plus or minus 0.5%. So when we're starting to look at the different components that are contributing to the uncertainty of that sensor, we can look at, we've got calibration standard uncertainty. So different folks are going to be using different reference standards to make sure that their power source is reliable. Here we typically use calorimetry. There's a couple other techniques. When it comes to temperature uncertainty, this is always can be difficult to lock down, and there can be a lot that goes into temperature control of a room to make sure that you're properly monitoring. Linearity uncertainty, can refer to the dynamic response of the device. So it could be in the case of a diode detector type of sensor where you're going to have different variations in measurement over the dynamic range, or like case here, we're doing direct RF sampling. So we're taking a look at the linearity of the analog to digital converter itself. Harmonic uncertainty, just making sure that the sensor can properly reject out of band unwanted signals. When it comes to repeatability, we're thinking, okay, pop the sensor out, back in, repeat a lot of measurements, see what kind of variations you're getting in a measurement that way. Mismatch is going to be due to just the small imperfections that are going to come with any coaxial structure. You're not always going to get it, exactly to 50 ohms. So you'll have small reflections that will even come off of the sensor that way. When you're looking at things like frequency interpolation, that's the idea of we're going to have different calibration points the sensor is going to be calibrated at, and well, we can't calibrate every exact frequency, every little frequency along a large band. So there's going to be some interpolation effects which can introduce some variation, as well as just the ability of the sensor to actually measure frequency of the source. So here I have a little example that's just showing when we're taking into account these different values that go into the uncertainty budget, because anytime you're going to be purchasing some off the shelf measurement device, or you're looking at really any device that might be in your system, there's going to be a lot of work that goes in on the manufacturer or on the vendor side to make sure that it's heavily characterized so you can have confidence in your measurements. So for example, if I take all those terms here, we're actually using a confidence factor K equals 2. So we have a 95% confidence that that measurement's going to fall within these bounds of plus or minus 5%. And actually, an interesting part here is when you're looking at the exact calibration frequencies themselves, we can remove things like a frequency interpolation uncertainty, and that can allow us to reduce this all the way down to this peak accuracy of peak uncertainty of plus or minus 0.5%. So while we continue to take a look at these pieces, we can see we're having different variations as we're looking over the dynamic range of an ADC. There's linearity components involved with that. How's the device going to perform with variations in temperature? The repeatability, like I was mentioning, you're going to have taken the sensor in and out of circuit, or even trying to use the interpolation effects of the measurement device. So the one thing though you might have noticed is, again, there's these little bands here. We're always taking into account, okay, we have a measurement here, but there can be some fluctuation in that. And as this can be really interesting discussion, but at the end of the day, it doesn't really leave the end user, you, the end user, with a whole lot that you can do. But it does start to help to get the wheels turning as to thinking about, oh, hey, I saw when Bird was limiting things like frequency and temperature, and how they were able to start pulling in the uncertainty. So, we do a lot of the hard work for you. We're trying to quantify and reduce those measurements so you can have the confidence. But let's take a look at some considerations you can make in your own testing to improve your measurements. And when I was looking at different sources of uncertainty preparing for this, I was seeing that really the big ones that always come to mind for me that I'm usually interacting with customers about are typically have to do with mismatch and harmonics. So this comes back to there's a few common configurations that I'm always working with customers and seeing, and that can be if they're doing some sort of RF generator transmitter connected into a through-line directional coupler cell sensor and then terminated into a dummy load. If they have an RF transmitter that's actually performing through the sensor out to an antenna, or in case of a lot of the manufacturing type environments, especially on the semiconductor side, I'll see guys even do some things like RF generator sensor, and then they have this matching network to help reduce some of the mismatch between the generator and the plasma chamber. And the big thing I keep in mind here is each of these cases is going to vary with their exposure to ambient temperature, what kind of power is you're outputting from your generator transmitter, what kind of connectors, cables are you using? Are they high precision? How many connectors and cables do you have in your system? Something like this where we have a sensor running to or a transmitter running to an antenna could easily be 100-foot run, from between the sensor and the antenna. So there's a lot of different pieces that can go into play here. And as the system complexity increases, or as your load starts to stray more from a standard impedance like 50 ohms, you're going to start seeing different mismatch effects start to show up. So Mismatch is really the idea of getting reflected power off of whatever inline system component you might have due to the impedances being different from the two components. So each time we add a new component, we're adding an additional opportunity for a reflection to occur. And when you're going to start considering this, it's again, any component you might have that's a through-line component in your system. And I'm thinking, cables, connectors, dummy loads, antennas, including the sensors. So even like this little diagram I have over here, we could think, the generator transmitter has got some characteristic impedance of approximately 50 ohms. The minute it comes into contact with another cable connector, there's going to be a very small amount of mismatch and some reflection. Again, as the other end of the interface is connecting from the cable to the sensor, we're going to get mismatches, and we're going to see this just about at every connection point. Now, in the higher quality RF components, there's going to be usually a lot more stable materials or better precision that's going to help to reduce these pieces. But let's take a look at mismatch as VSWR. This is a quantity you're typically going to see when people are characterizing mismatch, and this is simply referring to when you have an impedance mismatch between two components like that, you're going to have a forward and a reflected wave that are going to be interacting with each other. Now, in a case of if we had a VSWR of essentially infinity, or you could say 100 or whatever, a very large number to 1, we're talking about the reflected wave is essentially the same magnitude. All the power is being reflected back. We're getting points along the transmission line where we're actually having the two waves add together completely, and then other points where they're actually subtracting together, subtracting and just being eliminated. So that's this variation we can see here with the red dotted line. Now, when we're thinking a VSWR of 2 to 1, I bring this one up typically because, especially when I'm working with the guys in the semiconductor side of things, this is really where we do the cutoff on what our sensor can, we can have the assurance that it's going to maintain accuracy. We're going to talk about directivity here in a minute, but the idea of a VSWR 2 to 1 means you're going to get about 11.1% reflected power back just due to impedance mismatch. You can see we're starting to get a little less variation here. As we approach something like VSWR 1.15 to 1, this is what you're going to see a lot of times in different dummy loads, especially at lower frequencies. We're going to have a much smaller variation. Now we're talking about, instead of that 11% reflected power, now we're talking more 0.5% reflected power. And then the holy grail that we're all usually striving for is to get our components down to that perfect match, VSWR 1 to 1, so we don't have to worry about so much reflection. This isn't really a realistic case, but just to give you an idea, versus complete reflection. Now, I mentioned directivity and mismatch in the case of the sensor. Directivity is a term that I'm bringing up because when we're looking at these different mismatches being included due to different system components, and we're getting reflected power coming back at the sensor, this will play into the ability of the sensor, of a directional coupler style sensor primarily, to make an effective power measurement. And this is due to really directivity is the ability of the directional coupler, or that's the RF sampler used in this type of sensor. Again, I'm using the 7037 over here in the corner as an example. It's really the ability to isolate the forward wave, like we saw in the previous example, from the effects of that reflected wave. How cleanly can we sample that forward wave? And then again, when you're sampling the reflected portion, we're trying to see how well can we actually measure that reflected portion without the forward wave interfering. So that's helping us to build our VSWR measurements that will be included in devices that offer you a forward and reflected type of measurement. So in the case of here, we actually have, I have just two quick examples, which are going to be directivity of a coupler style sensor that's going to be 25 dB versus one of a 40 dB. Now, there's a little bit of math behind these pieces. We've got some of these directivity calculators on our website. You can do some searching and do some of that, but I just want to show this as an example. The actual end values when you're looking at these directivity pieces is we would have easily a VSWR of 1.33 to 1.7, and that can be a fairly large range. And when we're thinking of that in terms of the actual forward power, we're thinking, okay, 2.2% to 2.3%, so minus 2.2 plus 2.3. And so our forward power is doing okay for this directivity component, but you can see the reflected measurement is actually getting killed here. So in the case of this, where we have this 100-watt output, this results in this, around 98 watts versus 102 watts. Or in this case, if we're trying to measure this 4-watt signal precisely on the reflected path, we're going to have a lot of variation here. So in the case of the directivity a little bit higher at 40 dB, now we can see our VSWR numbers are much tighter. We're looking 1.47 to 1.53. And now this directivity, these errors due to this directivity are going to be much tighter. So plus or minus 0.4%, or in the case of the reflected power. So you got to keep in mind too, if we're having a small reflection, we're going to have what could be this 4-watt signal versus this giant almost 100-watt signal that's going on the forward path. So it can be a little bit more difficult to make those types of measurements on the reflected path. And so that's where, as we start to take a look at these different pieces like directivity, can help us understand, okay, how are these waves going to be interacting, and what kind of variation can I expect, or what kind of confidence can I have due to these types of mismatch errors. So in terms of cable connector mismatch, any cable connector you're going to be putting into your system, it's going to have its characteristic impedance built by the idea of you have the concentric circles. They're going to have a center conductor, and you'll have some dielectric medium, and then an outer conductor. All these pieces are coming together in such a way that you're forming this approximately 50 ohm impedance. Now, if you want to learn more about those pieces, I did talk a little bit more about impedance in a previous webinar I did on RF fundamentals, so feel free to check that back out. Today we're just going to keep moving along the idea of, we're going to have different pieces that come into play that are going to affect this VSWR of this inline component. And that can be anything from just the solidity of the connection between the male and female, or the male pin and the female receptacle on a connector like you would have on the input here, to just maybe there's a little bit of oxidation that's been building up on the surface that's now contributing, that's kind of throwing the impedance values off a little bit. We'll talk a little bit more about some mismatches due to problems here in just a moment. But just, you can see even just off the shelf, we're rating something like this with a VSWR value. And again, a good thing to always keep in mind when we're looking at cables and connectors, because we're talking about that relationship between the center conductor, dielectric medium in between, and an outer conductor. Things like temperature are going to play into making certain materials more lossy. Resistivity is going to increase over temperature. We're going to have some different effects coming into play there that can affect our measurement, especially like on a cable. Even when I was just looking through cables trying to get a rough idea for this presentation, usually when you're seeing someone describe a cable, they're not talking in terms of VSWR. They're talking in terms of attenuation per foot or per 100 feet. You can see here we're talking about attenuation in dB per 100 feet or per 100 meters. Now, again, we have that temperature range that we're able to use that around too. But we got to keep in mind, as things are heating up and cooling down, this can be due to ambient temperatures, or maybe we're pushing a lot of power through that connector or through that cable. Like in terms here, if we were at that full power of 25 kilowatts, we could really be heating that thing up and could be pushing us more to our bounds, to that higher loss value or to a higher VSWR. In terms of dummy loads, we can think, there's going to be a variety, especially depending on what kind of power levels you're trying to terminate. Are we trying to terminate 1,000 watts, 1 watt? I know some of you guys in the broadcast industry might easily be terminating, 50 kilowatts or 100 kilowatts. So again, we're thinking in terms of, there's this coaxial structure that's being put together we're trying to dump all this RF energy as heat. But as these structures are getting larger and there's more temperature variation coming into play, depending on, how close are you to the max power, what kind of ambient power levels or ambient temperatures are around you, we're going to have different things come into play that are going to make the performance of the load VSWR move around a little bit. But even here, we can just take a quick look. This is a much larger 1 kilowatt load. It's going to have VSWR about 1.1 from DC to 1 gigahertz versus something like this is going to be a much higher precision. Typically, if you're, this is going to be like an open short match type of termination. This is going to be used for calibration and of our Sitehawks and scalar network analyzer. So we have much better VSWR on this over a much broader frequency range. There's a lot of pieces that come into play when we're talking about why something might have a certain VSWR of a range or a power level, but it's just always good to consider what types of temperatures are they around. As the structure gets larger, and impedance can be maybe a little bit more difficult to maintain over a large band, maintaining this tight impedance, getting larger VSWR as a result. But also, when we're thinking of both those cables, connectors, or dummy loads, we're usually thinking of a much tighter VSWR, and that over a much broader range, where something, for example, like an antenna is going to have a sort of a band or several bands where performance will be ideal. And so like in the case of this antenna right here, where we're going to be measuring this VSWR value of less than about 1.5 over the desired frequency range of around 800 to 900 megahertz. So there, again, there's going to be different devices in your system that are going to have these frequency specific pieces and are going to have different VSWRs that are going to be occurring due to, especially in the case of an antenna, just where is it installed? Is that the ideal install location? Does it require a ground plane? Is there snow and ice building up on it or something? There's multiple things that can change the impedance of the antenna, resulting in that mismatch and creating a VSWR that might be a little more undesirable. So when we're thinking load mismatch, this is where I'm thinking, something like a dummy load that's going to be closer to your ideal match. Something like an antenna, it's going to be more moderate. When we're thinking loads, we're more around that 1.1, 1.15. Something with an antenna could, be more around the 1.5 to 2 VSWR range. And then something that's going to be more like a manufacturing process, like a capacitively coupled plasma chamber like this, or maybe if you have a very large inductive type of system like an MRI device. Now we have an impedance that's going to start to stray farther away from 50 ohms. So most of the time, all the systems we're working in, especially the comm side broadcast, we're thinking in terms of 50 ohms. We're not, we know there's small deviations around that. That's what we're characterizing with all these mismatch pieces. But as we start to stray towards other types of loads, different applications, that's where we're going to start to get impedances that are going to stray much farther away. The limited directivity or finite directivity of those coupler style sensors can be overwhelmed and can make the measurements have very large uncertainties about them. So in that case, we actually switch over something like a VI sensor, but I'll bring that up here in just a moment. First, I want to talk about, we were looking at some of the mismatch pieces associated with just the off-the-shelf component. We know, okay, coming right out of the factory, we've got an idea of where the performance is going to be on these different components. But a lot of times we're going to be actually seeing, what could be a much more significant mismatch from some sort of problem in the system. We might be able to tightly control some sort of calibration lab or calibration setup, but as soon as we start running cables, hundreds of feet up a tower, now we're introducing a lot more uncertainty to the system. So when we're thinking, different cable problems, this is where you're going to see, if something's loose or you have an intermittent connection, any type of dents and crimps and kinks, and I've seen deformation due to environmental factors. UV can be very damaging on these different types of pieces, or if things are getting hot and cold and causing some impedance changes. Clamps that might be holding these cables in place can really play a role in shifting that nice coaxial structure. Especially a big one is always anything with corrosion or water intrusion. That'll easily wildly change impedance. Anything with improper bend radius, where, like, for example, over here where we've got, this is definitely no longer a nice coaxial structure, so impedance is going to look pretty far off. When it comes to connectors, I've seen things like this. This is actually off of my Sighthawk that I had at my desk. Using a customer site, there was a small deviation on the center pin, and it resulted in a broken leafing on the female receptacle. So, there's little pieces like that can happen. I could have easily screwed it in and gone about my business, and then been wondering why my system was acting funny. Maybe, as you get back and away from the site. Improper center pin depth, that different ways these cables are being assembled, just making sure that things are being not too far in, the pin isn't sticking out too far, or make sure it's sticking out enough to ensure a good connection. Like the cables, water intrusion is always bad. Over tightening is a problem I see a lot. And again, you're going to be really jamming a center pin in there. It can be forcing it well past where it's supposed to go, and causing damage to the female receptacle or male pin, and can easily result in a broken piece like this. When I'm thinking mismatch in terms of antennas, I'm thinking, like for here where we've got icicles hanging off the thing, antennas are a very reactive type of structure. Anything that you're going to put around them or on them or near them can result in some weird effects. I see guys out there, especially on the broadcast side of things, that might be having these VSWR monitoring systems in place because they want to be able to detect when something with the antenna has changed, because maybe they live in a colder climate and there's icing or something with snow that has now happened. You could even have, depending on where your antenna is installed, a lot of these can be way up a tower on somewhere up on top of a hill, and they can easily experience things like wind damage. It can be ripped off and hanging to the side, and it's no longer in a good install location. Again, there's always the idea of corrosion that can play into these types of pieces and rapidly change impedance, surface resistivity. And then even things like for a dummy load, a lot of you guys that are performing your calibration over time, these the carbon on the surface of the resistor that's internal to these can start to get a little funky. You'll see it in the oil, inside of something like an oil dummy load, where the chemicals are actually being released due to the thermal effects. Some guys are overpowering them, end up in toasting these things. You'll see impedance start to drift over time on different loads just from heat and shifting around, especially in something like an oil load that's going to have these chemical components in it due to the oil that's inside. Overheating can also result in that. If you're performing something, a measurement in a place that maybe has a covering or something like that, that's not letting the unit radiate the heat away properly, or something that might just have a high ambient temperature. And actually, one that I've seen that's pretty interesting around the overheating side is I've seen guys that attach the sensor directly to the load, And when they're running at a higher power, they're actually getting a large thermal transfer from the load over to the sensor. And then as we were looking earlier, we were seeing, hey, temperature, we were trying to lock our sensor into that smaller temperature band to kind of pull the uncertainty in. So now if we're really dumping a bunch of thermal energy into that sensor, we can expect to now be sort of going outside of that 15 to 35 C like we saw earlier. So I've seen that lead to some accuracy issues as well. But we talked a lot about mismatch. That's usually the one I'm seeing coming up in a lot of these discussions. But actually another one I found that's pretty interesting, different customers have come to me with this, and it's always kind of cool to see. It's the idea of harmonics that are coming out of their generator or transmitter. They don't know it's there. They might be using a different style of sensor and then using ours as sort of a check. So they might be using one of our through line sensors here and then some sort of wider band terminating power sensor here. And where I really start to notice that affects what the difference of those two sensors come into play is, first off, there's limitations around the accuracy of the attenuation for different attenuators. I know you can buy more precision ones, but it's always a little bit trickier to completely nail down attenuation associated with attenuator, especially they're going to be thermally dependent and they're going to have variations over temperature. But something like a terminating style power sensor that might be measuring heat can easily be measuring anywhere from 100 kilohertz up to 6 gigahertz. So you could be measuring all kinds of harmonics that could be coming out of an RF generator transmitter, where on different through line devices that have the directional coupler style measurement are going to be more narrow band. And so they could have harmonics adding together constructively or destructively, kind of like when we were looking at the VSWR examples earlier. They can be adding together in those types of senses and resulting in some issues in the discrepancies between the two power sensors. So that's where I'll see guys do some low pass filtering to try to measure, or even a band pass filtering, to try to measure precisely around the frequency of interest that they want to look at. And just to put a bit of a visual to that, we could take a look at here where we're gonna have a fundamental in the dashed black line. We've got different third, fifth, seventh harmonics coming into play here, much smaller amplitude, but we can see they're starting to create some deviations in the actual waveform itself. And even over here, we can see, we're taking a couple harmonics into play. We can see how these different pieces are starting to add together and changing the actual shape of the waveform. So I've seen that come together, hurting people both constructively and destructively, and they'll see those variations in power measurements. So now that we talked a little bit about mismatch, got to touch on harmonics, we saw some things with directivity. Here a few things that we can consider to help reduce these uncertainty pieces in our measurement. A big one that always comes to mind right away for me is allowing time for the equipment to stabilize. So, I mean, there's going to be sensitive electronics that are going to be in these pieces of measurement equipment alongside of the just the thermal effects that your desired power level could be having on the equipment in the system. So again, that's the idea of, okay, when you plug your sensor in and you've got some dummy load attached, there's going to be heating up, especially if you're going at a higher power level, there's going to be heating of cables, connectors, the load itself, the sensor. There's going to be a lot of movement over that initial period of time when you first turn everything on. So it's always good to consider, trying to find some stability period and just wait until you get to something that's a little more stable. Another big one is don't always expect the different measurement errors and offsets to be identical at different, whether it's power levels or ambient temperatures or frequencies. And this comes back to the idea of, the VSWR of these different devices or mismatch of these different devices as they're heating up and cooling down, whether it's due to power levels or ambient temperature effects, there's going to be different movement happening, and that's pushing it further towards its maximum rated values for those pieces. And then even something like when we're thinking frequencies, we could be thinking like the image of the antenna where we had a frequency sweep and we were seeing the VSWR values over a larger range. So making sure that, you know, the performance is going to be what you desire at your particular frequency. You might have some variation around even over a performance band that you're looking for. So it's always good to consider connector and cable wear. A lot of people don't think about it, but there's typically a rated amount of mating cycles with different connectors. Something like an SMA that could be around like 500 mating cycles. Also, the idea you could think of the construction is going to be it's going to be screw on. There's going to be a lot more mechanical grinding and wear and tear that's happening with that versus something that's going to be more of a quick connect, almost like a BNC connector or an SQS for the guys that are in semi that will allow you to cleanly insert and remove these different connectors and reduce any sorts of mechanical wear. You know, especially if it's wearing on the plating of the connectors or just on the receptacles. Another consideration is just, you know, minimizing the times that a device needs to be disconnected or reconnected. I've seen different test setups that people have created where it can require a lot of connection or disconnection and reconnection from different places. If it's possible to arrange the equipment in such a way that allows you to only have to swap in just a small section of the whole piece rather than swapping all kinds of different pieces, that can always be good. Just this kind of goes back to, you know, partially on the cable wear or the connector wear and tear, but also on the idea of we saw that there was a repeatability component like in our sensors for our uncertainty budget. So, you know, again, it's the same idea, just, you know, keep an eye on your repeatability. Maintaining sensor calibration cycles. So this could be, you know, a lot of times, you know, recommendations like on our different sensors will do 6 months to a year, but, you know, just check with the manufacturer, just make sure you're staying within a rated calibration cycle. You know, there's a lot of work that goes into making these different types of measurements, and it'd be a little bit frustrating to go do all that effort and you know, your sensor has drifted out of some performance region that, you know, you expected, and you could be getting some more undesirable readings and not even know it. So also, you can always, you know, use filtering to eliminate harmonics or other types of unwanted signals, whether it's a low pass filter, band pass filter. A lot of times we just slap a low pass filter on there, try to get it so we're cutting away right there at the second harmonic, and then we can focus on the fundamental frequency of interest. This could be particularly interesting, especially on the more precision process side of things. I know different guys that are using, like on the semi side or semiconductor side, where they're using matchboxes. There can be some filtering techniques. You know, even the idea of just creating a good match over a smaller frequency range can result in the frequencies that are, or the powers that are actually getting through are what is desired. You know, some of the others are going to be filtered just by the nature of the matching network. Using the right sensor type for the right mismatch environment. I know this one we didn't really get to talk a whole lot about, but this comes down to the idea earlier I mentioned, hey, you know, not always are you around 50 ohms. So particularly when you're trying to measure higher power devices, especially something like a dynamic load like a plasma chamber, it's good to measure with a VI sensor. And I mean, if you're doing other things that are gonna have variations in impedance, you know, you can always do something with a vector network analyzer where you're taking into account these voltage, currents, phases, all these different pieces to accurately understand the impedance of a device. But really what we're talking about here is, you know, when we're thinking, you know, at power measurements, especially of a dynamic load that requires the power to actually be flowing through the system while you're taking a measurement. This was a measurement I had actually taken about a year ago at a customer I just had a 1356 generator. Again, there was that impedance matching network I was talking about, trying to reduce that mismatch. And then this is into that capacitively coupled load. This was a pulsed style of measurement, but you can see, we're getting that voltage, current, and phase, and then we can use that to calculate our power. And this idea can hold true for any non-standard load you might be trying to monitor, whether it's plasma chamber or some sort of inductive welding tool, or could be something maybe in an MRI active use case. But just always good to keep in mind, because that uncertainty is going to get too crazy with the directivity error on those coupler style measurements. So just to take a quick recap, we discussed the importance and applications around uncertainty, as well as defining, what exactly is uncertainty. We took a quick look at an uncertainty budget example of a sensor, just to try to see how, not only how a manufacturer is going to characterize it, but what other considerations can you make based on those pieces. We took a look at a couple of the most common uncertainties that I see, due to mismatch, and then also harmonics. And we took a quick look at some considerations for what you can do to improve your setups. So the key takeaway I really want you all to think about is, regardless of why you're trying to measure your RF power, it's important to understand what you can do to effectively measure it in your system. And so whether that's making sure that you're reducing directivity errors, or using a higher directivity device, or maybe using a different type of sensor that for these non-50 ohm loads. It's good that now that we got the ball rolling and we got you thinking, the topics here hopefully will help to identify areas of uncertainty in your different setups, so you can start to improve them and get a better sense over, or maybe that better confidence factor into the measurement you're making of your devices. So with that being said, going to get Michelle here in the loop, and I think we're going to do a couple questions. We still got a little bit of time here. So
Yeah.
I just want to thank everybody for coming out and listening to everything. I hope that was very useful. But all right, let's do a couple questions.
Okay. I think that was some great information. I kind of look back over the past couple of months. We've covered basics of RF. We've done power measurement accuracy. Now we've done uncertainty. We've looked at cable antenna basics, and I think it's all really coming together. We've even talked about designing communication systems. So for you guys who have not seen some of the other webinars we've done, or panel discussions, you can go to our website under resources and tools and watch them anytime or however many times you want. So, and we always look for feedback. So anytime there's a topic that you think we would be, you'd like to have us cover, please reach out to us. Okay, so let's take a couple of questions here. We actually have a specific question on the BDS2. He says, how about the uncertainty information of a BDS2? The accuracy of a BDS2 is different with a locked or unlocked system. So we would like to know how you can identify the accuracy of them.
So that's a good question. Let me back up here just a moment. I just want to pull up okay, so the device that I was measuring this item here with was a BDS2. And just to give a quick example, this actually, it has a through line portion of the sensor. There's a set of cables then that run from the sensor to a receiver that's actually doing all the high-speed processing analysis of the signal. So we can actually reduce the uncertainty of that whole piece of or that whole set of equipment by calibrating all those together as a system. And then we're actually taking into account any small phase variations or mismatch pieces that could be due to the connections on the cable, or performance pieces with the sensor. We have that all lumped into one calibration table now, and it allows us to effectively cut the uncertainty of what would be the standalone components in half. So we do see people use that quite often to try to get and squeeze a little bit extra accuracy out of their unit.
Okay, I hope
Yeah,
that
and
answers. Go
yeah,
ahead.
and Steve, that came from Kodo-san in Japan.
Oh,
So great to
hey,
see
how's
you
it
here,
going, Coda?
Kodo-san.
Okay, great. Um, Here's another one. Can I eliminate all of the uncertainties?
So that is that would be a nice thing, but we're always going to have some level of uncertainty associated with with anything that we're doing with our different system components or piece of equipment. Um, it's it's a it would be nice, but yeah, unfortunately, we're just never going to be able to tell something with 100% certainty. Just there's too many limitations on the measurement equipment itself, or just there's too many variables and factors that really play into real life to ever dial it all out. But the cool thing is, as we improve all the pieces of test equipment we have and continue to improve, building better, higher quality cables and connectors and measurement devices, we can really start to approach zero to the point where maybe though we haven't gotten rid of it completely, it's small enough that, hey, it doesn't really matter. So,
Okay.
yeah.
Let's see. We did a little more time. Says, what is the difference between error and uncertainty?
So, error is more of the, you could think of it as, you take a measurement and it is incorrect by some amount to a true value. So, even though it might be hard to measure it perfectly, there is this true value that a source is actually putting out, and whatever our measurement device is displaying, okay, there's going to be some offset, and that can be accounted for. But the idea is uncertainty is really, though, even though we've taken a measurement point and we have this piece of data, applying the guard band around it allows us to think of it more in terms of, okay, there's different uncertainties associated with this measurement. So we can't, even though we have a measurement that's showing up on, on our screen or on our device, there's still going to be, some pieces that are factoring into that, it could be within a small range. So yeah, it's really the idea of like the offset from the true value versus, the fuzziness around that value that we measured.